Hello. This video is going to be a short presentation on something very important called the passive sign convention. And I'm going to show you a couple examples of this as I go through this 10-minute video. The passive sign convention is a very important technique used to assign voltage polarity across passive elements, whether it be resistors, capacitors, or inductors when you're analyzing electric circuits. Note, using the passive sign convention is essential when you're writing either mesh, sometimes called loop equations, or node equations. If you do not use this technique, you will most likely not be able to get the correct answer to the problem when you're working out and analyzing the circuits. So let's discuss what the passive sign convention is and why it's so useful. I'm going to start with just a simple example here. I have 5 quick whiteboard slides to show you. If you have resistors in the circuit, which most of your circuits are going to consist of resistors and dependent and independent voltage and current sources, but we're talking about passive elements now, which is the resistors in most cases. If you sign direction of current in this direction through a resistor, what you have to do is put a plus on the side of the resistor where current enters and a negative where the current exits. Don't forget, current is the flow. It's the flow of charge carriers. If you assign direction through a resistor here in that direction, get in the habit as soon as you assign the direction, the voltage polarity would be plus as the current enters and negative when it comes out. If you decide you wanted to show the polarity down through a resistor, write the plus here and the minus here. And the truth of the matter is, when you work on these circuits, you can sign current in any direction you want. And you could be wrong. It'll all come out in the wash if you put in your passive sign convention. Let me show you what I mean. Let's say you decided to show the direction of current in that direction from right to left. Just make sure you put a plus there and a negative there. Current always enters the positive side of a passive element. It's called passive sign convention. What if you showed the current going in this direction through that resistor? You put a plus here and you put a minus there. And what if you showed current coming up through that resistor? Which you could. You make sure you put a plus at the bottom and you put a negative at the top. That's called the passive sign convention. Let's go to the second slide. For those of you that have had mesh analysis and loop analysis, let me continue. Let's say that you want to do mesh analysis on this first circuit in the upper left-hand corner, or loop analysis, whatever your instructor calls it. Let's say you assign a clockwise direction of current. Let's say you call that current I1. As soon as you show that current, you put a plus there and a minus there, a plus there and a minus there, and a plus there and a minus there. That's called the passive sign convention. What if your instructor has you draw it in a counterclockwise direction for that loop current? That's not the way I do it in class, but you could do it that way. Just make sure you put a plus there, a minus there, a plus there, a minus there, and a plus there and a minus there. Remember, the direction of current you assign enters passive element on the positive voltage polarity of that element, and it leaves on the negative. What about these circuits on the right here? Let's say you assign current going in that direction, and let's say you assign current going in that direction, and let's say you assign current going in that direction. Before you start your nodal analysis, you have to put a plus here and a minus there, and a plus here and a minus there, and a plus there and a minus there. Always show that passive sign convention. If you just happen to show current maybe going in this direction, And let's keep this current going in the same direction, but let's make this current come up. You can do that. You can assign those currents in that direction. But before you start writing your equations, make sure you put your plus there and a minus there, and your plus there and a minus there, and your plus at the bottom and the minus there. Matter of fact, as soon as I drew those arrows, I should have put in that polarity before I drew the next arrow. I should put in the polarity before I drew the third arrow. You should get in the habit of doing that. You have to get in the habit of doing that, or your problems most likely won't work out. Let's look at slide 3. Actual circuit. If you're doing mesh analysis or loop analysis on this loop here on the left-hand side, most likely your instructor is going to say clockwise, there's I1. As soon as you do that, put a plus there, a minus there, and a plus on that side and a minus there. And he'll probably have you draw a loop current clockwise direction, I2 there. For those of you that haven't had mesh or loop analysis yet, don't worry about this. Just put in the passive sign convention. You'll see how important it is later. As soon as you get that direction of I2, you put a plus there, you put a minus there, you put a plus there, and you put a minus there. You have to put the passive sign conventions in before you start analyzing your circuit. Let's do nodal analysis. Again, you might not know nodal analysis, but you sure can understand the concept I'm going to show you with passive sign convention. Let's say in this case right here, you're going to do nodal analysis, and you're going to assign this current in that direction. You're going to call it I1. Let's say you're going to call this current here in this direction. You're going to call it I2. Well, as soon as you draw an I1, put a plus to minus. As soon as you draw I2 arrow, put a plus to minus. And let's say usually you have that going to ground. I3. Put a plus there and put a minus there. Before you start the problem, you have to put that in. You could sign currents in different directions. It'll come out in the wash as long as you put the passive sign convention in. The importance of that, maybe I'll show you on the last slide for those of you that had nodal and mesh analysis. Let's go to the fourth. I'm just going to throw in a dependent source here on this problem. And what I'm going to do is I'm going to write a mesh for the problem on the left side. So I'm going to go around this here, and I'm going to call that I1. As soon as I do that, what I'm going to do is put a plus down here and put a minus up there. Notice that's opposite what the author has for polarity. So just keep that in mind when you get to your final answer. But what I would do is call that a clockwise direction, so you can use the techniques we used in the past. I2. You put your plus, oops, we had to go in that direction. We had to put a plus to minus there and had to put a plus to minus there. I didn't finish that first loop. In the second loop, on this side, I put a plus to minus because I2 goes in the opposite direction. I put a plus to minus there. That is very important that you put those in. In nodal analysis here, I want you to notice something very, very important. If you have, in this case, we have a voltage-controlled voltage source there on the right. And the author has given you what the voltage is for that voltage-controlled, that dependent voltage-controlled voltage source on the right. It's 5 times the voltage VO, and you can see where VO is. Notice in this problem, the author is telling you, or the person to come up with this circuit is telling you the direction of current in that left branch. That person is telling you that that current flows in this direction. Has to, because of the plus to minus here. So you already know I'd call that I1. I don't care about this current. I'd call that I2, plus to minus. And this current up here, let's do it in that direction. It doesn't have to be plus to minus. But notice, because of this, you're better served if you just keep that in mind and assign I1 in the correct direction. Because the author is giving you the voltage polarity across that resistor, that 4 ohm resistor. And finally, let's take a look at another circuit here. That's a current-controlled current source now. It has a dependent voltage source of 40 volts, and it has a current-controlled current source. The current in that dependent source is 4 times Ix, where you can see Ix is defined. So if I'm doing mesh analysis, this is what I do. I make my loop here, I call it I1. I make my loop here, I call it I2. I make my loop here, I call it I3. But notice the definition of I. As soon as I put, well, before I go to that, let's put my plus to minus there, let's put my plus to minus there, let's put my plus to minus here. Let's put my plus to minus there, and we have our plus to minus over here, which is what the author, how the author is defining VO. It's in the correct direction in this case, so I3 matches the correct direction. If it didn't, I'd just go ahead and not assume it clockwise, and I'd use that technique. And just keep in mind when you're done that the author had a different polarity assigned to VO, which could be right, depending on what you come out, what I3 comes out to be. Obviously, if I3 comes out to be a negative number, you assume the wrong direction. But in any event, the purpose of this particular lecture is to show you that that's the way that I would assign clockwise loop currents. But notice in this case what Ix is equal to. Ix in terms of I1 and I2. The author has Ix going down. And between the currents I1 and I2, I1 goes down, so I1 is the lead current. So Ix is I1 minus I2. That would be an important equation that you'd come up with for that controlling variable here on that current-controlled current source. If you look at nodal analysis over here on the right side, notice the direction of Ix is already given. So if you're coming up with an unknown voltage right here, V1, and with nodal analysis, that's one unknown voltage and the other unknown voltage there, you might be tempted to call it V2, but V2 would be a dummy variable, I call it. Why come up with a voltage of V2 when you know that voltage out there is V out? They give it to you here. And this is all the same point here. So don't put in what I call dummy variables. It just adds to extra equations. So that if you take a look at that, that's clearly V out or V naught. But the important thing here is conventional current. If I assign passive sign convention. If I assign current in that direction and I assign current in that direction, let's call this I1 and let's call this I2. Let's go ahead and just write the equation there. Let's do the whole nodal analysis equation, because out of the two, mesh and nodal is going to be the one that's going to be most useful. So my first level equation at node V1 by Kirchhoff's current law. Let's write the top level equation. Current, and the convention I use is currents coming in are positive and currents leaving are negative. So I end up with a plus I1 minus Ix minus I2 equals 0. And keep in mind, when I1 goes in that direction, I put a plus to minus in. Ix is given, so since Ix was given, I put a plus there and a minus there. And I2, I could have picked any direction I want, so I put a plus there and a minus there. The passive sign convention. And here's why it's so important. Because when you write the nodal analysis equation, the nodal equation at V1, and we go to what I call the second level equation here, and you come up with what I1 is equal to. I1 is always equal to the voltage on the more positive voltage minus the more negative voltage. So if you take a look for I1 up there, you start with the plus side of the resistor. That's why the passive sign convention is so important, because you end up with 40 minus V1. All that divided by 20. Take a look at that. That is your I1. Ix you start at the positive side for the 20 ohm resistor. That's Ix, so you get a minus, it's leaving, it's minus. What's Ix? Ix is V1 minus 0, well, it goes to ground, so V1 minus 0, divided by 20. And then finally, we have I2. I2, you start at the positive side, as you define current. So that's equal to a V1 minus V0 divided by 10 equals 0. I used the passive sign convention to write the second level equation in nodal analysis. Now, there's another equation we have to write at V out, but that's another lecture. It just takes a minute, but that's not to write that, but it's not the purpose of this lecture, so I'm not going to write the second equation. The only thing I will mention for those of you that do nodal analysis, when you look at the circuit and you label your currents and you put in your passive sign convention, don't jump to that equation first. Always write the first level equation. Always write that first level equation. It's the simplest, and it definitely gets you started. And then I think it's pretty easy for you to see, once you do that, how to come up with I1, how to come up with Ix, how to come up with I2. I hope this brief lecture on the passive sign convention helps you out when you analyze your circuits. It's a must to get in the habit of putting those plus and minuses in if you want to get the right answer to your circuits.